Hello, everyone. Hello, everyone. As introduced, I'm Benedikt Rudolph. I'm with DKIX. DKIX is an internet exchange operator based in Europe. And I'm still waiting to get the slides on the screen. I work with the research and development group, and over the last couple of months, I had the opportunity to look into BGP flow specification for route servers, especially in the context of IXPs. And for you internet engineers, BGP is the essential tool for interdomain routing. And if you look a bit closer, it's not only just one monolithic tool, it's a suite of tools. There are several BGP extensions, each of one that solves a different problem. And one of these extensions is BGP Flow Spec. What we have seen over the last years is that vendors implemented the RFC, software became ready, people are using it, but not everywhere. And maybe it's a good idea to start using it at an internet exchange. There also have been previous talks at NANOG about Flowspec, and I don't want to repeat them. I want to especially look at the situation at internet exchange points. So why would you use BGP Flow Specification? Some recap. It's a good tool to deal with malicious traffic. That's the #1 application for Flowspec. But you can also use it for other things. You can use it to direct traffic towards an analysis tool that you run in your network. You can use it to redirect traffic for IDS or for lawful intercept or whatever you need to do. Or you can use it to ensure QoS policy if you're running some special applications on your network. What it essentially does, it exposes the already present packet processing features, ACL, firewall, and so on, of your routers through BGP. Actions are based on n-tuple matching the fields of the IP packets. And it's easy to automate, similarly to the remote triggered blackholing that you already know to fight malicious traffic. Flowspec is easy to automate. There was a talk at NANOG 71 about Flowspec automation. You can dive in deeper there. This comes with because it's piggybacking on top of BGP. BGP has good automation support everywhere, so Flowspec. And it also leverages the best practices and policy controls that you have already in place for BGP. Like you're filtering what are you seeing, is that particular peer allowed to do this? Next hop validation is being done against the unicast routing. So you can implement it in a secure and senseful way. There's even some more information that I compiled for you on BGP Flowspec, but that's mostly repetition, is RFC 5575. And when it comes to the technical part, in the BGP protocol, there's a new network layer reachability information, which encodes all the flow rules in a bits way. So you have the source and destination prefix, a protocol port, and the action which is taken on that flow rule is encoded as a BGP extended community. Next to Flowspec, there's also some more traditional techniques around to mitigate DDoS. There's those ones you use in your local network, intradomain, and there's techniques that you can use interdomain, that you can use also in a more cooperative manner. So you're doing something and maybe others react based on things you're doing. Those techniques can be ordered into static or dynamic ones. So these are the classic ones. And of course, access control lists, manually editing ACLs is kind of static, and you can do it only on your hardware. Then there's remote triggered blackholing. This is more interdomain. You're announcing a blackhole to your upstream. Upstream's blocking traffic. But it's also kind of static because you don't see when the DDoS is ended. You have it in place, or you either don't have it in place. It's not so flexible. And then there comes Flowspec. Flowspec can be used in your internal system, but it can also be used interdomain. I'm not encouraging any use particularly, but I say it can be used in such ways. And it's quite dynamic because it's working on top of BGP. Let me give you a brief example how it could be working in the IXP setting. So, as you may know, volumetric DDoS is quite popular today, and the autonomous system D on the bottom is receiving a volumetric DDoS attack. It originates from autonomous system B and C. They're sending, for example, NTP amplification traffic, and autonomous system D wants to keep its service available, so he is announcing a discard rule for this particular host network that says essentially protocol NTP, I don't want it, please discard traffic. And maybe then the web server which runs on the same host is still available. The rule is announced towards the route server, and the route server propagates it to all the other peers in a very simple setting. The other peers would take up this Flowspec rule and load it in their router accordingly and stop sending this attack traffic. That's a very simple way of how it could be done. Yeah, and as you may know, on an IXP, many networks come together. There's some quite large IXPs, and as you are adding information to other people's routers, you need to be careful. And even the authors of the RFC warned about this. They say it could have impacts on performance. The storage space in the routers is limited. The number of elements that can be processed in those internet routers is limited. So you need to be careful in using Flowspec, especially if you're using automation. If you're doing it manually, the volume is low, okay, but when you're doing automation, you want to be careful. And we, as an operator of a reliable route server, want to make sure that if people start using it, that we can take up with a demand that is put on our systems. So to come from to design a scenario that we can reliably test if we can run a route server that supports Flowspec, we first need to perform an analysis, like what to expect if people start turning on Flowspec. So what number of Flowspec rules to expect per neighbor, what is the update frequency that we might be seeing, and because there's no Flowspec enabled currently, we need to look at other data that we have. So we looked at the data from remote triggered blackholing, and we kind of take it as a basis to estimate what would happen if we were using Flowspec. And we were interested in do our peers use it manually, or do they already have automation in place for remote triggered blackholing? And I will give answers to that right now. So we had a presentation at NANOG 67 with a scientific work of my colleagues from 2016, where we collected blackhole announcements and analyzed them. And I repeated the evaluation based on current data of 2017. So in a 3-month time frame, we saw about 23,000 announcements for blackhole routes. There's a quite stable number of /32 black holes included. It's 1,200. And there's also a stable number of less specifics, 31 until /18, about 50 networks. On the 2017 data, we see numbers increased by a bit. We're now seeing 1,750 black hole announcements. That's a 95th percentile of the amount. And then what kind of prefixes are announced? It's mainly host routes. It's mainly /32s, 97%, and they're very short-lived. We see that 50% live shorter than 3 hours. This is also confirmed by the current data. 95% of the ASNs have less than 5 black hole prefixes that they are sending. And at maximum, we're seeing 421 prefixes per ASN. We're not really sure if this data is representative for the entire internet, but that's what we're seeing at our Frankfurt exchange. And then I wanted to find out, is the activity that we're seeing, is it automated or manual? So I performed a clustering. We have 4 dimensions here. we have the amount of prefixes at the top. We have the amount of re-announcements. We have the mean lifetime and the mean time active. The lighter colors denote that there is a high amount of activity in that dimension, and the darker colors denote that there's a lower amount of activity in that dimension. So on the top left-hand corner here, we see there's some ASNs that have a high amount of prefixes, here also, but they also have a high amount of re-announcements. So that may be a clue that they're using some kind of automation. And there's this other part in the diagram that you can note where it's quite dark in every dimension. And this is a low amount of prefixes and a low amount of prefix activity. So those may be the ASNs that do not use automation. So it's a kind of 70% to 30% split. Okay, now that we gathered some data, we were just going out there and looking. Maybe somebody turned on Flowspec by accident, or maybe it's somewhere on by default. We're just looking. There's 3 steps. You have to have firmware support, namely multi-protocol BGP and the Flowspec capability. You need to have it enabled, and you need to negotiate it during the protocol handshake. So we analyzed a bunch of BGP open messages and looked for the corresponding AFI and SAFI indicators. That's what we did. And guess what? It's not turned on. We looked at the New York-based router that mainly had private peering, 81 BGP sessions, and they were non-enabled. And we looked at our DKIX Frankfurt route servers, looked through all the open messages, around about 900 BGP peers that we have over there, and we found non-enabled. That's not surprising. Yeah? Everyone is not enabling something that they don't need, but we were just curious and looked around. So even if it's supported, it's not enabled by accident. So actually what we hoped to see that there's a bunch of routers that have it turned on, so we know at least that a certain amount is supporting it. So this is still unknown to me. But I think the hardware which is currently out there does support it. So we didn't gather any test data from there. Next up is our route server setup. I will explain you the setup, and then I will explain to you the evaluation that we did. We're using BERT for our route servers. BERT is an open source routing daemon, and in December, version 2.0 appeared. That's a major refactoring of the software, and for the first time, multi-protocol BGP was included. Also, an integration for IPv4 and IPv6, and Flowspec support. And this basically made us have a look in it. BERT features a very expressive filter language, for example, to perform route validation. But however, there are certain limitations with regard to Flowspec. You cannot access the flow-specific fields in a flow route. You can only access the common BGP fields that all other BGP routes have. And what it is supporting right now, just a basic reflection of BGP Flowspec messages. So when you're using BERT as a real router, it cannot program the data plane, for example, the Linux kernel. But we're using it not for that purpose anyway. Then our test setup. We were dumping the routes that we're seeing from our peers at the route server into some files and preparing extra BGP configurations. And we were also taking the filtered and non-filtered routes in order that we can exercise our prefix filters in the BERT configuration. And then what we do is we replay those advertisements against a route server that is running our configuration. So the test setup is composed of 740 peers, 316,000 routes for 182,000 unique networks. And it's all run on dedicated servers. Okay, before we skip through or go through the evaluation, I will just briefly explain you what you can see there. I'm plotting CPU usage in red and memory consumption in blue. And in the beginning of one of those test runs, we are starting BERT. Then we look at the idle memory use. Then we start all the simulated peers and wait until the system converges. They're announcing the routes. Route server is processing the routes. Does quite a lot of work because CPU is here mainly at 100% because it has to do the prefix validation and so on. And then it reaches a convergent state. The route server is idle, and we can perform some additional commands. We can also see the memory that is used when the system is convergent. So this is the first scenario that we go into. Here we're using BERT version 2 with a Flowspec-enabled config. And we see it starts quite well. Then there's a phase where CPU is not at 100%. This is where the process is busy performing I/O, sending network packets, and so on. So in an ideal world, it would just top out flat 100% and then finish. Yeah, but compared to other tests that we have run in the past, it looks quite well. There's one particularly large neighbor that we simulate, and this takes a bit of time. That's maybe an outlier in this evaluation. So it takes 1,736 seconds. It's quite long, but it's okay. That's the thing that we're seeing in our production platform as well. And for comparison, we're running the current stable version of BERT. That's version 1.6.4, and it's a bit faster to converge. It also takes less initial memory and about the same memory when all peers are up. And then we also did a configuration BERT version 2 without Flowspec just to see if there's a difference. It took a bit longer for this to reach the convergent state. We also have this one neighbor that is delayed, but the numbers are the same as with Flowspec. So doing Flowspec on top of the setup doesn't really change anything. And there are other results that support this. You can investigate the BERT memory usage a bit more in detail with a special command that you can submit to the daemon. And here we have a table that outlines the memory use in idle state for all of the different data elements that BERT is keeping and in the convergent state. So we're seeing that BERT version 2 uses 44 megabytes more idle memory than compared to the old stable version, but that's not a big deal. And what is the effect of adding Flowspec to the setup? So when we're using BERT 2 with Flowspec, we're seeing some more amount of memory used for routing tables and more amount of memory used for the routing protocols when in convergent state. But all in all, that's not a real, that's the kind of result that we expected. The next aspect that I want to focus on is how does the BERT routing daemon interact with the BGP neighbors? And therefore, I basically captured the traffic on the interface to the peering LAN, and I wanted to measure how long does it take to propagate a Flowspec announcement. We're distributing a Flowspec rule to all of the 740 simulated neighbors, and the initial announce takes 19 milliseconds. This is the neighbor who announces the route is sending the packet. The route server is processing the packet until it sends the first update to one of its peers. And then it takes another 17.4 milliseconds to reach all the other peers. So in total, all peers got the update after 36.4 milliseconds. Interestingly, when you withdraw that Flowspec route, it's faster. It only takes 1.1 milliseconds, including the processing inside of BERT. And the propagation takes another 14.3 milliseconds, so it's done in 15 milliseconds. When you compare it to some ping times, it's quite good, I think. Now we had the single update The other thing that I looked at was performing a bulk update. So I kind of extrapolated the growth of black holes or Flowspec rules that we're seeing. 2,300 IPv4 rules, and I advertised all of them to our simulated route server. The initial announcement took quite long because of my method. I used BGP CLI interface and a bash script to announce all of those. There may be more clever ways to do it, so it took 1,500 seconds. That's not really representative, but that's just what I found out. More interesting are the two other things that I looked at. So now that the daemon learned all of those 2,000 Flowspec rules, I was interested what happens when I withdraw them. So I disabled the protocol in BERT, and the daemon had to withdraw all those routes for all of those neighbors, and it took the daemon to 34 seconds until all of this was done. Compared to other events that we have when I shut down other protocols, it's quite good. And Flowspec itself doesn't add any real overhead here. And at last, I re-announced all those Flowspec routes, so I brought the peer up again, and this takes 6 seconds. This is a bit faster because I only shut down the protocol in BERT, and I didn't shut down the BGP, and this is why mostly internal processing is going on. Interestingly, here, BERT allocated more memory, so it allocated around 8,000 kilobytes of memory. I don't really know, maybe it's caching something that was withdrawn in the past, but it's not a big deal. So that was basically the evaluation that I performed. Let's draw some conclusions out of this. We wanted to know, is the software that we're currently using ready? And it seems to me that it is ready. BERT itself and the Flowspec implementation, they seem to be ready for some kind of deployment. We don't know what the actual deployment will look like, but we know some tools are there. And we were testing in worst case conditions. So obviously, it's unrealistic to assume that all of your peers are Flowspec enabled. So my test scenario was just to configure every peer Flowspec enabled and test it. And scalability looks quite good. We're happy with what we're seeing, and there may be lots of interesting applications possible. Okay, that's basically the content that I prepared. As said, I used a few sources to prepare my slides, and now I'm happy to take questions or comments from you.
Barry Green from Akamai. So first question, do you have a script to take from the RIB into IP tables on a BERT implementation? ACL gets deployed on a Unix box.
So when I understood you correctly, you were asking if we're actually filtering traffic based on the ACLs that we could generate from Flowspec?
So Flowspec is pushing a policy. The policy is impacting the way you put ACLs on the edge of a network. So you're deploying, an ACL on the edge of a network. So is there a function in BERT that does that?
No, and BERT is, and that's why
I understand what BERT is.
That's why we start to. That's why we were able to evaluate, because we don't need that function. You would need that function if you were using BERT as an edge router for your network. But we're using it as a route server, and therefore we don't need it. So BERT is currently not able to push routes to generate ACLs in IP tables, for example, on Linux. There's no support.
So my suggestion for the next phase of testing is pull the vendors in, because the warning in the draft and your scaling parameters you have to look at is testing your ability of pushing ACLs down to TCAMs, network processors, memory areas on edge equipment that is in high, 10, 100 gig sort of range of equipment. We knew when we wrote Flowspec what the scaling parameters of BGP was. I mean, we're doing multi-protocol BGP for a long time in big networks, and so we understand the scaling parameters about that. That's why it was chosen at the point. The question mark has always been, what is your performance envelope, on the edge of your network during a particular incident, right? But as, Don's sitting over here, as was brought up at the NANOG in San Jose, we already have operators building Flowspec-based DOS collectives to protect infrastructure, to protect critical infrastructure. So I would suggest people go back to the San Jose NANOG, pull up those materials, or grab Don Smith, who's over there, and talk to them about CenturyLink and AT&T and some of the others who are working on these collectives. So people are looking at it as a production use with it. But one of the big gaps we're seeing in industry is, you guys could be in a position where you say, okay, Cisco, Juniper, Huawei, Alcatel, Nokia, get your butts over here into this test lab. Let's run this test. Let's see what the performance envelope is. So there's public data. Don's coming up. Don may say, oh yeah, we've been doing this test inside CenturyLink, but.
Yeah, looks interesting. So.
No, we're not there yet. Sorry. Don Smith, CenturyLink. There's a couple of areas that we're concerned about right now. I'm working on an RFC to limit some of the things that you can do with Flowspec. So between me and AT&T, we agreed one of the things we want to do is just drops. No rate limits, no QoS, none of that. All I want you to do is send me drops. But I can't do that. My router doesn't support that. Next, I need some way to measure this, because someday my management's going to say, Don, how much bad traffic did you keep off the network this week? And I can say, I don't know. That's not a good answer. I don't know is not an answer. So we need SNMP counters. This is the router vendors, guys. We need SNMP counters and stuff like that so I can measure each Flowspec rule and say, I dropped this much for AT&T yesterday. And we need all this driving into a ticketing system. So we're working on that actually with XMBGP. But we need all these things before you can really do it between two peers, let alone doing it between 18 different people all talking to one route server.
Okay.
Sorry, I'm preaching. I'm not even asking a question. Sorry.
No worries. It's good to see that there's other efforts going on as well, and we're open. If we can help, we'll do.
Eric Rosenberry from NWAX. So you tested this. You took a certain number of IP addresses that were currently being blackhole routed to kind of get your baseline of how many Flowspec messages. I was wondering, since with Flowspec you would have a lot more granularity to the specific ports and kind of ACL level controls. What do you think the chances people would use that to a much greater degree, rather than just, hey, I'm blackhole routing this one IP that's under attack, but now I'm like getting down to port level stuff, and so you might have like a significantly increased number of advertisements being made. And did you consider that at all in your analysis? Yeah, so we kind of integrated it in a way that I just extrapolated the numbers. So from the message format, if a Flowspec message can have a variable length because maybe several actions attached to one message, but this is the same than when you are sending just more Flowspec messages in total. So so in terms of scaling, it's not a big issue. And the setting that I looked at was just for Flowspec messages, so there's no processing on the individual message involved. So it just takes the message and copies it out to all of the peers. So even if I would have tried different ports or different actions, the result would. Because you can have multiple kind of actions or multiple things within one message. So as far as Bird was concerned, it only is processing.
Yeah, and I tried it just to prove to myself that it works. But for the particular setup that I tested, I just used one message and different IP addresses to generate.
Thank you.
Hi, Rich Compton, Charter. I was just curious, do you have a system to detect the DDoS attacks? And if so, I was wondering if you could describe it. And all of the Flowspec testing that you're doing, are you detecting the DDoS attacks and then automatically generating the Flowspec rules?
So we're running an internet exchange, so we're just the connectivity provider, basically. And we're not actively detecting DDoS that is going on. So you may got the idea some things because I looked at the remote triggered blackholing data that we're seeing. So this is basically peers of us or customers of us that instruct our peering platform to drop traffic on their behalf. And it doesn't need to be DDoS at all. So you can even use the remote triggered blackholing functionality to just shut off an IP address out of your block on the exchange. That there is a remote triggered blackhauling announcement doesn't necessarily mean that this IP address is under attack, but it's an indicator. Yeah, okay. I hope that's an answer to this.
Does this work? Yep. Job Snyders, NTT Communications. I work for a global routed internet exchange, and DDoS attacks and automatically react to them. So I see no reason why DKICs cannot do the same.
Yeah, well, this is a very early stage of our work on this. We just wanted to know, since we heavily rely on BERT as a route server, if the software is ready. And doing this analysis, it seems that it's ready. And maybe we will come up with a system that's similar to what you suggested in the future, but I can't promise anything on that right now, because I was just looking at the software that's currently out there and if it could be done. Thanks, Joe.
Okay, and we're going to cut the mics with Matt. Go ahead, Matt.
Matt Pitaco, simple question. With BERT, if you have mismatched NLRI information, one peer says I'm sending Flowspec, other peer isn't interested in hearing Flowspec, does BERT do the right thing? Does it get confused? What happens in a situation like that?
So if BGP Flow Spec isn't part of the handshake, then it doesn't forward the messages. And there's basically, think of it that there's a separate path in the route server for Flowspec, similarly to other multi-protocol extensions of BGP. So it's entirely separate from the unicast routing.
Okay, so you can have sort of asymmetric peer A to route server NLRIs, peer B doesn't accept it, route server will still pass along the particular families that it will listen for.
No, it doesn't pass it on, it just keeps them.
Oh, okay, got it. Thank you.
Yeah.
Awesome. Thank you, Benedict.